Welcome back, physics fans. Today, we are going to talk about the DeBroglie wavelength. You may recall that it was Einstein who first postulated that light sometimes acts as a particle and other times as a wave. A French graduate student named DeBroglie theorized that this dualism extends to electrons as well, and similarly to all objects that have mass. One of the early triumphs of the DeBroglie's hypothesis was to explain the quantization of the energy states of a hydrogen atom, which resolved an outstanding issue with the Bohr model. DeBroglie conceptualized an electron bound to a hydrogen nucleus as a circular standing wave, as shown in figure 6.18 in your textbook. Just like a standing wave on a string, only certain electron wavelengths can produce circular harmonics. These harmonics relate to the energy level of the electron, and the wavelength also gives us information about the radius of the orbital. One interesting consequence of this theory is that the electron bound to a nucleus does not exist in a specific location, but is instead spread out in an orbital shell. Experimental confirmation of the DeBroglie hypothesis came soon after, in 1927. Davison and Germer, two physicists at Bell Telephone Labs, were conducting an experiment in which they would bombard a nickel surface with electrons. In heating and cooling their sample, they inadvertently created a regular crystalline structure in the nickel. When they measured the distribution of scattered electrons, they were surprised to see a diffraction pattern. Similar diffraction patterns had been observed for electromagnetic radiation, but never particles that had mass. This indicated that the electrons were somehow interfering with one another, just as waves would. At the time of their experiment, neither Davison nor Germer were aware of DeBroglie's work, but they immediately recognized the importance of their results. These results were soon put forward as proof of the validity of matter waves. The DeBroglie wavelength in meters of an object is calculated as the Planck constant divided by the object's linear momentum. Another interesting result of this theory is that all objects have a calculable DeBroglie wavelength. The reason that we do not observe the wave-like properties of, say, a ping pong ball moving at 5 meters a second is that the Planck constant is so small that the wavelength of such an object is on the order of 10 to the negative 32 meters. In order to observe a ping pong ball diffraction pattern, we would need to pass this through an aperture of approximately the same order of magnitude, which is clearly impossible. However, the DeBroglie hypothesis has been experimentally confirmed many times, with electrons, neutrons, and more recently, multi-atom molecules. In 1999, a research group from Austria published a particularly dramatic demonstration of matter wave diffraction by passing fullerenes, each composed of 60 carbon atoms, through a 100 nanometer grating. For showing that matter has wave-like properties, DeBroglie was awarded the Nobel Prize in 1929 and Davison in 1937. If you would like to know more, check out the article in Nature on fullerene diffraction, or if you have specific questions, feel free to ask your instructor. See you next time.